Chapter 4. Measures of Variability. We mentioned in the previous chapter that distributions of data include shape, center, and spread. Variability is a measure of the spread of the distribution. Common measures of variability include the range, the variance, and the standard deviation. Let's take a look at the range. The range is the difference between the maximum of our data and the minimum of our data. For example, with the observations 3, 5, 9, 6, and 8, the maximum value is 9 and the minimum value is 3. That gives us a range of 9 minus 3, which is equal to 6. The range gives us a basic overall measure of spread. However, it is limited because it only involves two numbers. It essentially involves the minimum and the maximum and ignores all other values. The range is highly affected by outliers. There is also something called the interquartile range, or the IQR, where the IQR is equal to Q3, or the third quartile, minus Q1, or the first quartile. If you think about the box plots that we drew in a previous chapter, Q3 represents the top of the box and Q1 represents the bottom of the box, giving us the IQR representing the range of that box, which is the middle 50% of the data, ignoring the highest 25% of the data and the lowest 25% of the data. There is even something called a semi-interquartile range, which essentially is just the IQR divided by 2. The variance is another measure of variability, which uses all observations in its computation. The population variance is slightly different in its formula than is the sample variance. Unless specified otherwise, we will always be dealing with the sample variance. The population variance is found by taking the deviations from the mean, squaring them, adding them all up, and dividing by the count. The sample variance is found by finding the deviations from the sample mean, squaring them, adding them all up, and dividing by the count minus 1. And as you can see, the population variance is represented by a lowercase sigma with a superscript 2, referred to as sigma squared. The sample variance is represented by a lowercase letter s and a superscript 2, or s squared. Now let's look at an example. Here we have a set of data for 5 different hospitals. The sample mean is found to be 30. The deviations are found by subtracting that sample mean from each of the observations. 40 minus the 30 gives us 10. 20 minus the 30 gives us negative 10. We then square all of those deviations and add them all up. That sum of the squared deviations is then divided by the count minus 1. The variance is then computed as 100 in this case. The standard deviation is defined as the typical distance between each data value and the mean. The population standard deviation, represented by the lowercase letter sigma, can be found by simply taking the square root of the variance. So if you know the variance, you can take the square root of it to get the standard deviation. Conversely, if you know the standard deviation, you can square it to get the variance. The same is true for the sample standard deviation. The standard deviation is used extensively in statistical analyses. If you consider the difference between the variance and the standard deviation, using that square root doesn't seem to make much of a difference in the general concept. Which of those two values seems more reasonable? If we look at the definition, the typical distance between each data value and the mean, that makes sense. The variance would be defined as the typical distance between each data value and the mean squared. So that squared aspect, which is necessary so that the deviations don't all add up to 0, which would be a very uninteresting statistic, kind of complicates the definition. It makes more sense that we are considering the typical distance between each data value and the mean, and that is the definition of the standard deviation. So as far as interpretation goes, The standard deviation seems to make more sense than the variance, but both of them are used extensively in statistical analyses. The coefficient of variation is a measure of relative volatility. The population coefficient of variation is found by taking the population standard deviation and dividing it by the population mean, then multiplying by 100%. The sample coefficient of variation is found the same way as the population value, except by using sample statistics. The coefficient of variation is used extensively in business and economics. Now let's look at some mathematical considerations. We looked at the effects of adding or subtracting a constant from a mean. Now we'll look at what effect it has on a variance or a standard deviation. Adding or subtracting a constant changes measures of centrality, but it does not affect the measures of variability. Why not? Adding a constant simply shifts our data in the positive direction on the number line. Subtracting a constant simply shifts our data in the negative direction on our number line, but it shifts all the data the same amount. It does not make the data more or less spread out. If we multiply or divide by a constant, the measure of variability will change. Multiplying or dividing every observation by a constant is equivalent to multiplying or dividing the variance of the original observation by the square of that constant. And multiplying or dividing every observation by a constant is equivalent to multiplying or dividing the standard deviation of the original observations by that constant. Now we will look at the inferential properties of the range, variance, and standard deviation. Bias refers to the systematic difference between the sample statistic and its associated population parameter. A statistic is considered biased if it is consistently greater than or consistently less than its population parameter. A statistic is considered unbiased if, on average, it is equal to its population parameter. The sample mean and the sample variance are both unbiased. The sample standard deviation, however, is biased. So what we're saying down here is that the expected value of our sample mean is our population mean. The expected value of our sample variance is our population variance, but the expected value of our sample standard deviation is not equal to our population standard deviation. In summary, the range, variance, and standard deviation are common measures of variability. The sample mean and sample variance are unbiased. The sample standard deviation, however, is biased. And that is the end of Chapter 4, Measures of Variability.